22CS492, Foundation and Future of Virtual Reality, Artificial Intelligence, and Massively Multi-User Online Role-Playing Games. We continue today our discussion on the foundations of artificial intelligence, namely the theory of machine learning. We've discussed important aspects such as VC dimension and shattering, and we learned about the important Sauer-Shelach lemma. And today we're going to see how all this connects and relates to computability and complexity of machine learning. And this presentation will be given by Jehi. So Jehi, you have got the spotlight, microphone, and you should be able to share the screen.
Okay. Okay, do you see my slides and do you hear my voice? I don't know this works. Okay, thank you. Hello everyone. My name is Hwang Jae-hee, and today I'm going to present about PAC learnability and its complexity. Maybe you have never heard about this notation PAC learnability before, even if you had taken machine learning course. And yes, as you know, this topic is related to theoretical machine learning. So this presentation requires a lot of mathematics. Actually, this presentation consists 100% mathematics. If you are not familiar with mathematics, then this presentation would be not that interesting and quite hard to understand. And as you know, Professor mentioned, these presentations was further from VC dimension and Sauer's lemma. So in this presentation, I suggest a relationship between VC dimension and PAC learnability and Sauer's lemma. So this presentation goes further from previous presentations and use higher mathematics. So I think this presentation is quite hard. Also, I will try my best to explain this easily, but it may not be enough. And I think that I am not that much talented at teaching something, but I'll try my best. So let's get started. This is the contents of my presentation. First, I will introduce some basic mathematics, which is required to understand the definition of PAC learnability. And second, I will introduce the definition of PAC learnability and some examples. And third, I will introduce the extension of PAC learnability and its relationship between that and VC dimension, which is one of the topics for previous presentations. And this is my final goal of this presentation. And finally, I will briefly summarize this presentation. So first, I will introduce some basic mathematical notations, which is necessary to understand the presentation. For this part, I think this is quite easy for many students because who know about this basic mathematics, then this quite be boring. So this part is not that much hard. So let's get started. The first thing I wanted to introduce is epsilon delta definition, calculus 1. Maybe all of you may have one experience of studying this while taking calculus 1 course, and also for me too. Let's see the definition. A function f is defined on a set x of real numbers, has the limit L at x0. In other words, limit x to x0 fx equals L. If for any positive epsilon, there exists corresponding delta from epsilon, such that absolute value of fx minus L less than epsilon whenever x in x and absolute value of x minus x0 is delta. The main part is this, as you know well. It means there exists delta corresponding to any positive epsilon. So why epsilon delta argument is important? Because it provides delta for every positive epsilon, regardless of the magnitude of epsilon. We can set epsilon as very big, like 100, or very small, like 10 to the minus 100, or whatever, regardless of the magnitude epsilon, we get some positive delta from epsilon. In other words, we can think that there exists a function f from epsilon to delta such that it satisfies the condition. Some of you can think that why this definition is important for we learn PAC learnability. Actually, I don't use the exact definition of limit as epsilon delta argument, but as you know, in higher level mathematics, we use similar techniques to describe some higher definitions. So I think this introduction can help to understand this. I will explain this about later. The next thing I wanted to introduce is a basic definition of probability and statistics. Let's look at this definition. The set S of possible outcomes of an experiment are way that in each trial of experiment and only the outcomes, events in the set will occur. We call the set S a sample space for the experiment. Each element S is called a simple outcome or simple event. And an event E is defined to be any subset of S, including the empty set and sample space S. An event E is a simple event if it contains only one element, and a compound event if it contains more than one element. We say that an event E occurs if any of the simple event E in E occurs. Maybe all of you may know about this, so let's quickly skip this. And another definition is about the probability. Let's look at this. And given a probability assignment for the simple events in sample space S, we define the probability of arbitrary event E, denoted as PE. We will use a lot these notations and as follows. If E is the empty set, then PE equals 0. And if E is a simple event, in other words, E is equal to this, then probability of event E is this as defined previously. And if E is a compound event, the probability of E is the sum of the probability of all the simple events in. And if E is the sample space S, then this is equal to this, and which is equal to 1. This is easy, and I will suggest a very easy example. In a family with 3 children, excluding multiple births, what is the probability of having exactly 2 girls? Assume that boy is as likely as a girl at each birth. In other words, the probability of each situation is exactly 50%. So the answer is, first we determine the sample space S like this. And since a boy is as likely as girl at each birth, each of the 8 outcomes in S is equally likely. So each outcome has probability 1/8. And there exists only 3 cases like this. Thus, the probability of having exactly 2 girls are 1/8 times 3 equals 3/8. And let's move on to the other definition, which is mean or expectation. The expected value, also called the expectation or mean of random variable, is its average value weighted by its probability distribution. The expected value or mean of random variable x is written as EX. We will use these definitions much times later. And similarly, I suggest a very easy example. What is the expectation value of rolling a 6-sided die? This is very easy example. So the mean of the discrete random variable is defined as this, where x equals this set. Therefore, we can calculate the expected value as sum of these 6 elements, and this is equal to 3.5. So this was the first part of my presentation, and until now it is quite very easy, right? So let's move on to the main part of presentation, the definition of PAC learnability. From now, I will introduce some new definitions, maybe new for almost all of students. And so it would be hard to understand all the materials. So please listen carefully about these parts. Before we move on the direct learnability, we need to understand of new notations. the first thing I will introduce about is X and Y, which is this, and we note by X the set of possible examples or instances. X is also called, sometimes referred to as input space, and the set of all possible labels or target values is denoted as Y. Intuitively, if you like this, you can assume that X is input and Y is output. Note that set X is just a set, so it does not have other limitations. We can set X as just a finished set or infinite set, which can be uncountably infinite, like subspace of R to the N or something else. So let's move to the next slide. Also, to make the problems easier, like previous presentations, we will limit ourselves to the case where Y is reduced into two labels, like this set, which corresponds to the so-called as binary classification. Now I introduce another definition. This might be quite confusing. A concept C is a mapping. A mapping is equal to kind of functions, a mapping from X to Y. And a concept class is a set of concepts we may wish to learn at, and it is denoted by large C. This might be confusing, but this is very important definition for later slides, so I explain this precisely. You can think that a concept is just a function from X to Y, and a concept class is a set of concepts, which means this is set of functions, which is we may wish to learn. Also, assume that we are planning to learn algorithm through machine learning. Then for this case, concept class is kind of ideal algorithm, which is we wish to learn. And assume that examples are identically and independently distributed, which is called as IID, according to some fixed but unknown distribution D. This might be also confusing, but intuitively, this definition is like independent variables in probability theory. In other words, you can think that this is similar to mutually independent variables. Now I introduce another definition. We call a fixed set of possible concepts as a hypothesis set H. Recall that concept is kind of function from X to Y, X to dy. Then what is the difference between hypothesis set and concept class? The answer is hypothesis set is just like the definition of this word. Hypothesis set can be different from concept class because concept class is set of answers, as I mentioned, and hypothesis set is just a set of possible concepts. And that's why this is called a hypothesis set. Now you may understand the difference between hypothesis set and concept class. Now we move on to complicated definition of learning problem. A learner considers a hypothesis set H, which might not necessarily coincide with C, as I mentioned before. It receives a sample S drawn independently and identically distributed according to distribution D, which stands for distributions as well as the labels CX1 to ... CXM, which are based on a specific target concept C in C to learn. A learning problem is a task to use the label sample S to select hypothesis HS in H that has a small error with respect to the concept C. So consider a set of a hypothesis set which has elements H1, H2, ... and there exists a target element C in concept class. Note that all elements in a hypothesis set and elements in a concept class is a mapping, which has an input as X and returns label Y. We choose the best hypothesis, which has the least error to C. In other words, similar to C, which is located in a concept class. Intuitively, we can assume that C in C is a goal model to learn, and H in H is an incomplete model. Then how can we measure the error terms between H and C? So I suggest new definitions. I introduce very a lot definitions. I suggest how to measure the error terms between H and C. First, we look at the generalization error, which is widely used after these slides. Let's look at this. Given a hypothesis H in H, target concept C in C, and an underlying distribution D, the generalization error or risk of H is defined by R to the H, and this is equal to this, and which can be written as the expectation of this. You may not similar with this notation, and this is the indicator function of the event W. And this is kind of binary function which returns 1 for if the condition omega holds and returns 0 otherwise. Also, this notation means that the elements in the input space satisfies the IID condition, which is identically and independently distributed condition mentioned before. So, and let's look at the empirical error. Given a hypothesis H in H, target concept C in C, and a sample S is like this, the empirical error or empirical risk of H is defined by this. You can think that if you see these terms, then you can think that this is kind of similar to average of generalization error, and I think that is okay. So now we finally move on to definition of PAC-Learning. It took quite a long time. The following introduces the probability approximately correct learning framework. So let's look at this. A concept class C is said to be PAC learnable if there exists an algorithm A and a polynomial function such that for any positive epsilon and positive delta, for all distributions dx and for any target concept C in C, the following holds for any sample size greater than polynomial of these arguments, and which satisfies this condition. If algorithm A further runs in polynomial time of these arguments, then C is said to be efficiently PAC learnable. When such algorithm A exists, it is called PAC learning algorithm C. So this definition is quite complicated, so I explain this more precisely. Recall that this term R is the error term I mentioned in this slide. So we say that some problem is PAC learnable if for every positive delta and epsilon, like mentioned in this, there exists a lower bound of polynomial function of number of inputs. M, did you find the M? M is located in this. This stands for the number of input values. Anyway, for large M satisfies these conditions. In other words, enough large inputs, the probability of low error, low means less than epsilon, is greater than this value, or minus delta. Also note that we assume epsilon and delta is arbitrary positive number. Intuitively, in one sentence summary, PAC learnable equals there exists some kind of efficient algorithm which returns quite correct. What is the definition of quite correct is this, which satisfies this condition. I know that this definition is very hard to understand at once, so I tried to find some figures about the definition of PAC learnability. But as you know, the definition of this is quite abstract, so I couldn't find it. So I made some kind of diagram of this PAC learnable. So let's think about that. I said that some problem concept class C is said to be PAC learnable. There exists an algorithm. So consider that we have some learning algorithm, that we have some training samples, like product space like S is X times Y, and we set control parameters, these terms, which is mentioned in this. These terms are reset like, as I mentioned in previous epsilon delta argument, this is, we can arbitrarily set. So if we set as epsilon as very big or very small, but the important part is this, whatever we set the epsilon and delta, it should satisfy this condition. So this learning algorithm takes input as these values, and we set the control parameters. Then if this learning algorithm runs, then we can get on hypothesis, which is a mapping from x to the y, and we evaluate this hypothesis as this is quite correct or not, and it is evaluated by this term, which is probability of generalization error is less than equal to these terms, and which satisfies these conditions. If this hypothesis satisfies this condition, or if this holds, then we can say that, oh, your hypothesis is quite correct. So this is good algorithm. So we can say that this is PAC learning algorithm. And if for some learning problem, if this good algorithm exists, then we say that the problem is PAC learnable. I hope that this explanation helps to understand, but I know that this is very hard, so I suggest an example to understand this PAC learnability. So consider the case where the set of instances are points in the plane x equals r squared, and the concept class C is the set of all axis aligned rectangles lying in R squared. The learning problem consists of determining with all small error target axis aligned rectangle using labeled training sample. I will show that the concept class of axis aligned rectangles is PAC learnable. These figures shows the situation of this problem. Suppose that this blue rectangle is a target concept. I said that target concept is the algorithm that we wish to learn. So this is kind of answer. And circles represent training instances like these circles. And blue circles is a point labeled with 1, since it falls within the blue rectangle R. And others are red and labeled with 0. Our goal is training this hypothesis or rectangle R prime. So I explained this more precisely. So I suggest that the concept class of axis aligned rectangles is PAC learnable. The proof of this is quite long, so please listen carefully. To show that the concept class is PAC learnable, we describe a simple PAC learning algorithm A. Given a labeled sample S, the algorithm consists of returning the tightest axis aligned rectangle R prime, RS, containing the points labeled with 1. See this figure? I said that returning the tightest axis aligned, and this figure explains the situation. Now I think you understand the situation intuitively. So let's move on to the next step. Let R in C be a target concept. Fixed positive epsilon. Let PR denote the probability mass of the region defined by R. That is the probability that a point randomly drawn according to D falls within R. Since errors made by our algorithm can be due only to points falling inside R, we can assume that the probability is greater than epsilon. We can define 4 rectangular regions R1 to R along the size of R with probability at least epsilon over 4. These regions can be constructed by starting with the full rectangle R and then decreasing the size by moving one side as much as possible while keeping a distribution mass of at least epsilon over 4. If you do not understand my word, then see this figure. What I wanted to say is we can set 4 regions like this, R1 to R4, such that probability over distribution D of falling under such a strip is not more than epsilon over 4. So what I wanted to explain is these rectangles are very small at first, and we extend these rectangles, extend. So until when it do not exist the probability of epsilon over 4. So we make this R1 as just small, and we repeat this 4 times, and this is the situation. And Now let's see this more mathematically rigorously. In the previous slide, this slide is just a explanation of let R, R, B, and T real values defining R equals L to the R times B to the T. Then, for example, the left rectangle R4 is defined by this L to the S4 times B to the T, with S4 is infimum of S such that probability of L to the S times B to the T exists epsilon over. You may not familiar with the infimum if you not taken the analysis course. Infimum is greatest lower bound. It is similar to minimum element, but it is quite different. The probability of region R4, which is equal to L to the S4 times B to the T obtained from R4 by excluding the rightmost side, is at epsilon over. And we can do similar way to define our R1, R2, and R3 as like this. So as a result, we can write the probability of generalization error greater than epsilon as union of these terms. And trivially, these union of four terms are less than equal to summation of four terms. And why this is less than equal? Because these are double counted these regions. So this is less than equal. Anyway, and by the previous definition, this probability is less than equal to 1 minus epsilon over 4. And as we said, there exists m independent points, so we can write as this. And by this inequality, this can be proven by easy calculus. You know, this term is less than equal to this term. Now, for any positive delta, to ensure that probability of error is less than equal to delta, we can impose that this equation is logically equivalent to this equation with easy algebra. Thus, for any positive epsilon and delta, if the sample size m is greater than this, then this probability is less than delta. And if the size m is greater than this, which proves that the concept class of axis-aligned rectangles is PAC learnable, and this is PAC learning algorithm. I know that it is almost impossible to understand whole proof at once because it was very hard for me when I was studying this. So I briefly summarize the main ideas of this proof. The goal of this learning problem is find a concept which has a small generalization error. However, it is impossible to construct exact blue rectangles because we do not have much more information about that. So we have information of these points, so which is described like points in this figure. So what should we do? We plan to construct a tightest rectangle as a hypothesis, and this theorem claims such algorithm is PAC learning algorithm. And then why it is PAC learning algorithm? It is because for any positive epsilon and delta, we can construct a function which grows slower than polynomial function, which satisfies this condition from the definition of PAC learnability. Do you remember the definition of PAC learnability? The following holds for any sample size m greater than this term. As you know, this algorithm function grows slower than any other polynomial. So this is why the learning problem satisfies the condition for PAC learnability. I hope this explanation helps to understand this. Until now, I introduced the definition of PAC learning and one example of that. And now I'm going to introduce its extension. We generalize the definition of PAC learning, which is called as agnostic PAC learning. Let H be a hypothesis set. A is an agnostic PAC learning algorithm if there exists a polynomial function such that for any positive epsilon and positive delta, for all distributions d over s, the following holds for any sample size n greater than polynomial of these arguments, and which satisfies this condition. If A further runs in polynomial time of these arguments, then it is said to be an efficient agnostic PAC learning algorithm. It seems quite similar to the previous definition PAC learning. So I have one question. What is the exact difference between agnostic PAC learning and PAC learning? Recall the definition of the word agnostic in Korean, 불가지론. You can understand this as there does not exist the exact solution. Do you see the difference? I think the main difference between PAC learning and agnostic PAC learning is this term, which is not in just PAC learning algorithm. Then what is the meaning of this term? Recall that R is a generalization error, and this means this term stands for the nearest solution of an element of concept class. So this totally means the probability of a generalization error between a hypothesis and the nearest solution exceeds epsilon. So the next part I wanted to introduce is the VC dimension, which was one of the topics last week's presentation. So let's do a quick review of it. First, we need to know about the growth function. The growth function is a function for set of natural numbers to set of natural numbers for hypothesis set H is defined like this. This mathematical equations quite looks complicated, but you can think like this. Growth function is the maximum number of distinct ways in which m points can be classified using hypothesis in H. Each one of these distinct classification is called dichotomy, and thus the growth function counts the number of dichotomies, and that are realized by the hypothesis. Now we move on to the VC dimension. As you know, the VC dimension of hypothesis set H is size of the largest set that can be shared by H, and VC dimension of H is defined like this. Do you remember the definition of word shader? I hope you remember this because I don't have enough time to explain this, so I will assume that you understand these notations. And remember the very previous presentation about Sauer's lemma. Now I introduce Sauer's lemma. Let H be a hypothesis set with VC dimension of this hypothesis is equal to D. Then for all natural numbers n, the following equality holds. So I have one question. Sauer's lemma suggests an upper bound of the generalization error, and this is a relationship between the PAC learnability and Sauer's lemma. But how and why is this important? So I'm going to introduce about this importance of the Sauer's lemma. So I'm going to explain this more precisely. The significance of Sauer's lemma can be seen by the following theorem, which remarkably shows that growth function only exhibits two types of behavior. If VC dimension is finite, this is finite, and in which case growth function of hypothesis HM is big O notations of m to the d. Or if VC dimension is infinite, in which case the growth function is equal to e to the n. This actually I plan to describe about this theorem, but as you know, this theorem was presented by previous presentation by Sarah, so I skip this theorem. The proof of this theorem includes some mathematical techniques, but as you know, we can intuitively know this. How? Because we know that this combination function consists multiple of m minus l dot 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 or d times, so it is at most m to the d. So the actual proof is this, but I skip this. The important part is this. Important part is if VC dimension is finite, then growth function is at most polynomial of this m, which is polynomial, and otherwise it is exponential e to the n. Now I introduce this theorem, which suggests an upper bound generalization error. This theorem is quite complicated. Let H be a family of functions taking values in these two values with VC dimension D. Then for any positive delta with probability at least 1 minus delta, the following holds for all hypotheses H in H. Recall that this term is generalization error and this term is empirical error. So generalization error is upper bounded on empirical error plus this term. In other words, the form of this generalization bound is empirical error plus to these terms. The theorem looks weird, and also I don't have enough time to explain the exact proof of this theorem. So just remember that with Sauer's lemma, we can construct an upper bound for growth function of a hypothesis, and also an upper bound of the generalization error. Until now, I presented an upper bound on the generalization error. Then how about the lower bound? What if there does not exist enough lower bound for any learning algorithms? Now I suggest this big picture. In some situation, this really happens. In other words, I will introduce the condition which is not agnostic PAC learnable. Now I introduce this important theorem. Because of the time issue, I cannot introduce the exact proof of this theorem. Sorry about that. If you are interested in this topic, you can find the actual proof at the book of Foundations of Machine Learning, second edition, chapter 3. I will introduce this book in reference. And now I introduce about this theorem. Let H be a hypothesis set with VC dimension is greater than 1. Then for any positive m which is greater than 1, greater or than equal to 1, and any learning algorithm A, there exists a distribution d over x to the y, x times y, such that which satisfies these conditions. Equivalently, for any learning algorithm, the sample complexity verifies m is greater than this term. Did you find the difference between the definition of agnostic PAC learnability and this inequality? The different part is this part and this part. This part was actually minimum, and this is changed to infimum. But I don't think. Of course, minimum and infimum are different notations, but that is not important to understand this material. So another different part is this equality. This was originally less than equal. This is changed to greater. Recall the definition of agnostic PAC learnability. For any positive delta and epsilon, there exists some appropriate polynomial function such that when m is greater than equal to that, then this holds. But look at this. If we set epsilon and delta small enough for some big m and d, agnostic PAC learnability doesn't hold because this is not less than equal to original epsilon term. So I explained this more precisely. So we can, from previous theorem, we can got immediately this corollary, which is my main purpose of this presentation. With an infinite VC dimension, agnostic PAC learning is not possible. The proof is this, and the previous theorem shows that for any algorithm A in the non-realizable case, there exists a bad distribution S such that the error of the hypothesis returned by algorithm A is a constant times of this term with some constant probability. The VC dimension appears as a critical quantity in learning in this general setting as well. In particular, with an infinite VC dimension, agnostic PAC learning is not possible. Also, this theorem is my main goal of this presentation. So I hope understood well, but I know that this is very hard to understand. So now this presentation. So let X be the input space, and let Y be the set of target values. The learning problem is to find the hypothesis H in H with small generalization error. RH equals the probability of hypothesis is not equal to Y, which is element of concept class, and this is equal to the value of the expectation of this indicator function, which has an event as these terms. Hypothesis does not equal to Y. Now recall the definition of PAC learnability. Now I explain this one more time. Concept class C is said to be PAC learnable if there exists an algorithm A and a polynomial function such that for any positive epsilon and positive delta for all distributions over dx, and for any target concept C in C, the following holds for any sample size m which is greater than equal to this polynomial of these arguments, which satisfies this condition. If algorithm A further runs in polynomial time of these arguments, then C is said to be efficiently PAC learnable. When such an algorithm A exists, then it is called a PAC learning algorithm for C. And I suggest an example of this PAC learnable problem. This theorem states that the concept class of axis-aligned rectangles in R squared is PAC learnable. The proof is quite complicated and long, as you remember. So in this summary, I briefly explained the main idea of proof. The main idea of proof is we can construct a function which is a logarithmic function which is less than equal to polynomial, so such that it satisfies the below condition. So it satisfies the condition for PAC learnability. So this algorithm is PAC learning algorithm. So this learning problem is PAC learnable. After I suggest this example, I introduced some kind of extension of PAC learning, which is agnostic PAC learning. Let H be a hypothesis set, and algorithm A is an agnostic PAC learning algorithm if there exists a polynomial function such that for any positive epsilon and positive delta, all distributions P over S, the following holds for any sample size M is greater than equal to these terms, and which satisfies this condition. And the important part is here, which is different from the previous definition of PAC learnability, which means that this means that there does not exist exact answer in hypothesis set. So we choose the nearest answer from the hypothesis set. And also I wanted to introduce the relationship between this agnostic PAC learnability and VC dimension, which is one of topics for previous presentations. So I quickly introduced the definition of VC dimension. The VC dimension of a hypothesis set H is the size of the graded set that can be shattered by H. And finally, I introduced this theorem, which states on infinite VC dimension, agnostic PAC learning is not possible. The proof was quite complicated, so I introduced the main ideas of the theorem. And this is end of my presentation, and I refer to the textbook, Foundations of Machine Learning, second edition a lot, especially for chapter 2 and first part of chapter 3. And also I refer to Wikipedia, and the course held in 2021 fall in KAIST, computational learning theory, which is taught by Professor Hong-Seok Yang. So if you are interested in this topic of PAC learnability and theoretical machine learning, you can learn about much more materials from this website. And this is end of my presentation, and thank you for listening.
Yes, thank you so very much. Okay, and as usual, We're now going to take a short break, 3 to 5 minutes, for you to digest and to come up with questions and discussion points about the content, not yet about the quality, but about the content. So please take that opportunity of the break to create and find questions, things that you did not understand or that you want to have explained further, or comments about the content. Welcome back after the break. And now is the time and opportunity to ask questions and to provide comments about the content of this presentation about PAC learnability. And I would like to make the start by, could you share the slides once again? The definition of PAC learnability, right? So just you said it, but I'd like to re-emphasize that. So PAC is short for probably, approximately, correct. So that's a formalization of when is a machine learning problem learned correctly, right? So usually when you look into the literature, usually when some problem has been learned by an AI, this is demonstrated empirically. People make tests and run benchmarks. This is kind of what corresponds to the heuristics in computer science, in algorithm theory, not an algorithm, but a heuristic. But here we have a rigorous definition. And this definition is kind of like similar to randomized algorithm, which is something we will discuss maybe next semester in CS500 advanced algorithms. What can we expect from a randomized algorithm? Not to be correct always, right? Because there's always a chance for the random choices, the coin flips, to be disadvantages. And this is also reflected here. And this is the best we can hope for in machine learning, probably correct, depending on the samples. This is what the probability symbol here refers to. Let me see whether I can add here some comment here. This is the probability symbol, right? This is a, can you see that? Does that work in Zoom? So it's probably correct. And the probability here refers to the sample, right? So the sample size here, that means during the learning phase, the algorithm makes samples. So this is kind of like supervised learning as opposed to unsupervised learning. The algorithm asks, here, I've made this sample. Now please tell me which of the points in the sample have the property and which do not have the property. And this is something that then the user kind of has to answer to the algorithm during the training, to the learning phase. Right, so it's not like the user can provide the sample, but it's the algorithm during the learning phase that chooses the sample and then asks the user. Maybe this is a little bit similar to you know, all this in Google, this what is it called? When you ask, when a website tries to find out whether you're a robot or not, you're often asked to classify 9 images, right? Which of these images do show a ship and which don't? Which images show a bus and which don't? 9 images, right? And what you're secretly doing when you answer these queries to prove that you're not a robot, actually you're training an AI machine learning in Google, right? So this is exactly what is happening here. The AI comes up with a sample and then asks you humans to classify the points in that sample, which ones contain both and which ones don't, right? So that's about the probability part, the sampling part, and yeah, we can only hope that this is correct with high probability. High probability means probability 1 minus delta, where delta is here arbitrary but fixed, right? So you see that here for any epsilon and for any delta, arbitrary but fixed with respect to the asymptotics. And the second part in PAC-Learning is the approximately correct, right? That's here, approximately correct. And that refers to the that the probability of error should be small. And here, this is the epsilon, right? So we don't expect it to be always correct with certain probability, but approximately correct, and epsilon is kind of the approximation error. And we'll discuss that aspect further in the next talk when we talk about approximation capabilities of a special class of learning algorithms, namely neural networks, which is kind of popular, but still be important to be aware that this is not neural networks are just one class of learning algorithms. Okay, so yeah, that were some additional remarks from my behalf. And now, if you have questions, please go ahead and ask your questions now. No questions? Everything clear? Okay, then I'm going to ask you guys. Yes or no?
Yeah, it's actually fun, but I have more or less like a general question. Like just for me personally, like it has like a lot of mathematical stuff in the past presentations, which I can more or less follow, but I do also have like a hard time understanding all of it, to be honest. So I'm kind of wondering, like with respect to the essay we will have to write at some point, because we're like we're going through the proofs of different like lemmas and definitions as well. This is why I'm kind of getting lost, like what is like the key thing I should remember or take away in the essays, or what I should summarize or write about in the essay about like the mathematical things with
Actually,
respect to the topic.
I didn't expect that you or understand all the materials in this presentation, because I took a lot of time to study these materials about a week. So I think that it is impossible to understand all the materials in just 40 minutes presentation. So I hope that you understand just the definitions of PAC-Learning and why is PAC-Learning is important, and the relationship between the previous presentations, VC dimensions and Sauer's lemma. So I think just that is it is enough to understand my presentations. So if you didn't understand well about the mathematical proofs about my presentation, then you can just read my summary part, which summarizes just the definitions without mathematical proofs. So I think that would be enough to understand some materials of that. And for the definitions of PAC learnability, I think I made this diagram, and I hope that this is helpful to understand the definition of PAC learnability.
Could you maybe, because unfortunately I had to join a little later because I was delayed by my class before, so I missed like the beginning of your presentation, and then I had like a little bit of struggle to like get inside of your presentation. Maybe just quickly summarize for me, like as you were saying, like why is PAC learning important, like in artificial intelligence, or what basically the definition is a little bit about?
Actually, I just researched about just the definitions of PAC learnability, so I don't know well about how these PAC learnability are used in some kind of industrial departments. So I don't know about that, but I know that definitions of PAC learning is it is kind of decision problem, like we distinguish the PAC learnable problems and not PAC learnable problems. So how we can define that? Then it is based on this learning algorithm. If kind of this learning algorithm exists, then we say that the learning problem is PAC learnable, and otherwise it is not PAC learnable. And I explained it on example. Axis aligned rectangle is PAC learnable. Yes. I hope this helps to understand materials.
Thanks. Maybe another like general remark to all the speakers before. Could you be so kind to maybe upload the slides that could maybe help to just kind of get the entire picture, because they're very closely connected. I think so far only the first speaker's person has landed in the slide.
So you want the file this presentation?
Mm-hmm.
I can send you this PPT file. Oh, actually, I think we can share this PPT slide for every student.
Yeah, I think usually, like for the last block, we used to send the slides to the professor, and then he uploads it on the website so that everyone can access it. So maybe also kind request to the speakers before.
Okay, I will send this PPT after this slide to professor.
Thank you.
Yes, indeed. Some of you still owe me your slides from the first part. And yeah, also for the second part, let's collect all your slides and let me upload them on the course webpage. Very good suggestion. Thank you. Right, and why is PAC learning important? It's important because it's a definition, finally, right? If you think about it, the way machine learning is taught, it's usually here's some problem, here's a neural network, and the neural network solves that well enough, right? But there's never been any definition, so one could not even talk about whether some problem is learnable or not learnable. So this is kind of like the corresponding counterpart to computability and complexity theory in classical computer science. The fact that there exist undecidable problems is a very important observation by Turing. And now we have a theorem which says there exist problems which cannot be learned at all. So if your attempt in training a neural network doesn't seem to work, then there's a fundamental reason behind that. It's not your fault. It's because the problem is not learnable. Yeah, actually, I have also a question, right? So based on the theorems that you presented here, there seems to be kind of like a phase transition, right? So when the VC dimension is infinite, then the problem cannot be learned at all, right? And if the VC dimension is finite, then the problem can be learned in polynomial time, right? So the VC dimension enters as exponent in the asymptotic asymptotics. So either not learnable at all or polynomial learnable. Nothing in between, like in classical complexity, there's like exponential and many more NP, all this classical. But here it seems to be a very strict separation. This is what sometimes be called a phase transition, either that or that, but nothing in between. Is that correct, or did I miss something?
Actually, I studied the first part of this textbook, so I don't know well about in detail, but the theorem says that it is not PAC learnable if VC dimension is infinite. So I think that there exists some kind of cases that VC dimension is finite, but it is also not PAC learnable. But I'm not sure about the exact case, but it is just in my opinion. I will study later.
Okay. Other questions? Comments? Okay, then let's move on to the part where you provide comments and feedback about the quality and style of the presentation. And I pause the recording here. This is off the record. So time is up. Any closing, concluding remarks, comments? None? Okay, then let's thank Jahi once again. Thank you so much. Then that's all for today. I would like to ask Tolera to stay online. So we're discussing the next talk, and the rest of the class is dismissed. Goodbye.
Thank you.